everyone, I'm Dr. Rizwana, working as a Professor of Physics in Institute of Aeronautical Engineering. Today our topic of discussion is about a very important optoelectronic device, and that device is photodiode. So today we are going to discuss about a photodiode and of course different types of photodiode, which are PIN and Avalanche photodiode. So what exactly is a photodiode? Now, in my previous video, I have discussed about a diode. So what exactly is a diode? Diode is nothing but a PN junction. So what is PN junction? Where we are going to combine P-type and N-type semiconductors. Suppose I have taken P-type semiconductor and N-type semiconductor. So we know that in P-type semiconductor, what are the majority charge carriers? Majority charge carriers are holes. And in N-type semiconductor, majority charge carriers are electrons. So here we have majority charge carriers as electrons. And once PN junction is formed, we know that, once PN junction is formed, we have a diffusion of charge carriers taking place. And because of this diffusion of charge carriers, there is a formation of depletion layer across the junction. So here, when we talk about this depletion layer, and this depletion layer, it is going to play a very important role when we talk about this optoelectronic device known as photodiode. So that's why first we should get familiar with this depletion layer and what exactly we have in the depletion layer. We are going to recollect quickly. We know that once PN junction is formed, okay, so if this is P side of PN junction and this is N side of PN junction. So here we have holes, and then here we have on the N side we have electrons. Right, and of course this is the region which is separating P-type and N-type materials. Now what we'll observe here is, of course, because of diffusion we have migration of holes from P region to N region. And once these holes go to N region, what they'll do, they'll form positive donor ions. They become immobile positive ions. Similarly, once electrons get diffused from N side to P side, what they'll do, they'll become acceptor negative ions, which are immobile electrons. So here, after this, what will happen under equilibrium condition? Because of these immobile charges which are separated, a region is formed, and that region, what exactly is this region called as? This region, it is called as depletion layer. So this region, it is called as depletion layer. So this region, it is called as depletion layer. And why it is called depletion layer? Because in this layer we are depleted of charge carriers. So there are no charge carriers. All of them are immobile charge carriers without any energy. And of course, a voltage is also developed. That voltage, it is called as barrier voltage, or simply it is called potential barrier, which prevents further diffusion of charge carriers. So once PN junction is formed, there is a formation of junction or depletion layer in between the P-type and N-type semiconductor PN junction. Now, talking about this photodiode. So in photodiode, as I have told you, there is one important role played by this depletion layer. Now first, when we talk about this photodiode, and of course, what is a diode? This particular PN junction formed, it is nothing but a junction diode. Simply it is called as diode. And how we are going to represent this diode? We represent it by taking one triangle and then one vertical line. And this triangle, it represents P type of the PN junction, and this vertical line, it represents N type of PN junction. So this is the symbol for our diode. And what you will observe here is in photodiode, of course, we are calling it as special type of PN junction device because it comes under optoelectronic device. And what it will do, it will generate current. So it is going to generate current when it is exposed to light. So here, what we are saying here is it's a diode. And if I expose this diode to light, so if I make light fall on this diode, then what this diode is going to do, it is going to increase its current. So it is going to generate current. Or if you talk in terms of this transformation of energy, so what is input I am giving here? Input is my light energy, and what is the output we are getting? We are getting electrical energy, or which is nothing but current. So here we have change of energy, we have transition of energy or conversion of light energy into electrical energy. So this also we can say that it's a transducer. What are transducers? Which will convert one form of energy to another form of energy. So here input I am giving in the form of light, and output I am getting in the form of current, which is nothing but electrical energy. And as you can see, there is conversion of light to electrical. So this photodiode, it comes under optoelectronic device. So this will come under optoelectronic device. Okay, opto, it stands for light. Electronic, it gives rise to current. So here input is light and output is current. Or where we talk about conversion of light to electrical or electrical to light, then such devices, they are called as optoelectronic devices. So this photodiode, it will come under optoelectronic device, where it will convert light energy into electrical energy. And here, because of course, as I told you, they'll come under transducer. And what is the name given to this photodiode? It is also called as photodetector, or it is also called as photosensor. So it is called as photodetector, or it is also called as photosensor. And one thing what we have to understand here is this photodiode, it operates in reverse biased mode. So this photodiode, it is going to operate in reverse biased diode. So we will take reversed biased PN junction diode. Here we are focusing completely on reverse bias PN junction diode. And what you will observe here is this reverse bias PN junction diode, what it will do, it will convert light energy into electrical energy. Now, before going in detail what exactly is the principle of this photodiode, first we'll try to understand what exactly is reverse bias diode, and we'll try to recollect what are the VI characteristics of a diode, normal junction diode. So when we talk about this diode, so here when we are talking about diode and its VI characteristic. So first, when we talk about forward bias diode, what we'll do, simply in forward bias diode, we'll take PN junction, and then what is biasing of a diode? We know that biasing of a diode is nothing but where we connect P type of PN junction to positive terminal of battery, and then N type of PN junction, it is connected to negative terminal of battery. So biasing is nothing but applying external voltage. And here if we apply our external voltage in such a way that P type of PN junction, it is connected to positive terminal, and N type of PN junction is connected to negative terminal, this particular phenomena, it is called as forward biasing. So this is called as forward biasing, and we know that when we forward bias a PN junction, then what happens to its depletion layer? Its depletion layer will be decreased. So if you take a variable input supply, input voltage, so as you keep on increasing your voltage, then what happens to the barrier voltage in case of forward biasing? Slowly it will decrease, and then at one stage, at one particular voltage, your potential barrier will be completely eliminated, and there will be large current flowing across the junction. And when you talk about its VI characteristics, suppose if I take voltage on x-axis and then current on y-axis, and usually current in forward biasing, it will be in milliamps. So it will be in milliamps, and this is what curve we are going to get when we forward bias PN junction diode. And we'll observe that during forward biasing, your diode, it will act as a conductor, and in that conductor state, there is large amount of current flowing across the junction. So there is no problem with current flowing when we forward bias a diode. But same diode, if it is reverse biased. So same diode, if we reverse bias it, So what we'll observe here is during reverse biasing, in this case, how we'll connect our external voltage. So in case of reverse biasing, P type of PN junction, it is connected to negative terminal, and then N type of PN junction, it is connected to positive terminal. So this is called as reverse biasing. So what is reverse biasing? In reverse biasing, P type of diode, it is connected to negative terminal, and N type of diode, it is connected to positive terminal of battery. And once we take PN junction in reverse biasing mode, what happens here? We'll observe that, of course, in P type we have lot of holes, in N type we have lot of electrons, and these electrons, what they'll do, they get attracted towards the positive terminal of battery, and they'll start going away from this depletion layer. Here we have depletion layer, right? And if this PN junction, if it is connected in such a way that N type is connected to negative terminal and P type is connected to this N type is connected to positive terminal and P type is connected to negative terminal, then these electrons, they are attracted towards the positive terminal of battery, and these holes, they are attracted towards the negative terminal of battery. Then what happens to depletion layer? Depletion layer, it will be increased. So when we reverse bias a PN junction, then what happens to potential barrier? Potential barrier, or you can simply say that it's a depletion layer. So what happens to potential barrier? Potential barrier will be increased. So here we have potential barrier being increased. And when we talk about the flow of current, because as you can see, there is, what do you mean by potential barrier being increased? It means that there is increase in the number of immobile charge carriers. So in this depletion layer, number of immobile holes and immobile electrons is going to increase. So that's why, because there is no flow of charge carriers, so that's why what we'll observe here is when PN junction is reverse bias, it is taken as an insulator. So here you can say that a diode, it is a unilateral device where during forward biasing it will act as a conductor, and during reverse biasing it will act as insulator. And when it is reverse bias, usually say that it is an insulator which will not conduct any current. And but what we'll say here is there is small current flowing because of minority carriers. And when we take this reverse bias characteristic, suppose I have applied this reverse voltage, okay, and then if I take this reverse current, and this reverse current, it will be very small. If your forward current, it is in milliamps, then reverse current, it will be in microamps. And what we'll observe here is this current, sorry, if it has to be negative voltage. So if you take your reverse voltage, and if you take our reverse current, which is in microamps, then we'll observe that current will be very, very small. So there will be small flow of current. And when we go for very high reverse bias voltage, then there is sudden increase in reverse current. But till large amount of reverse bias voltage, reverse current is very, very small. So because this reverse current is very, very small, so that's why we'll say that reverse bias diode is an insulator. But in photodiode, what we are doing, here also we are taking our photodiode, we are taking our reverse bias diode, and our intention is to increase. So what we are trying to do, we are trying to increase this reverse current. And how we are trying to increase reverse current? By exposing our reverse bias diode to light. That is what we are going to get. So here, as you can see, reverse current is small. If I expose this to light intensity, then you will observe that reverse current is going to increase. So we are trying to make reverse bias diode a conductor, or we are trying to increase reverse saturation current, reverse current. Okay, when your diode is reverse bias, that is the main intention in photodiode. So as you can see, so what is the main principle of photodiode? Main principle of photodiode is photoelectric effect. So what is photoelectric effect? As you can see here, photo, where we talk about light, electric, we talk about current. So here reverse bias diode, when it is exposed to light, then there is increase in reverse current. So here, as you can see, the operating principle of photodiode is when the junction, okay, is illuminated, then current starts flowing through it. And as you can see here, only minority current flows through the device when certain reverse potential is applied to it. So whatever small current we are getting, that is because of minority charge carriers, and we are increasing current by exposing it to light. And what exactly is the symbol for diode? So if you see here, so here in this case, symbol for diode is, so if you talk about the symbol for diode, here we have, so as you can see, we have taken normal triangle and vertical line. So here we have triangle and vertical line, and this is a symbol for normal diode. Then what I am doing, I am just putting two arrows going inside, which are just going inside the diode. So this is the symbol for photodiode. It is to show that you are exposing this diode to light. So we are exposing this diode to light, and of course our output will be current, and this symbol, it is for photodiode. And as you can see in this figure, we are trying to show this PN junction being in reverse mode. And in order to show that flow of current, what we have done, we have kept a resistor in this circuit. So this is P-type and this is N-type, and this P-type, it is connected to negative terminal of battery, and this N-type, it is connected to positive terminal. And as you can see here, we have a depletion layer, and usually where we'll make light to fall on this PN junction diode, we'll make our light to fall in the depletion layer or across the junction. So here we are focusing light in this junction layer. Once light, and here we have immobile charge carriers, once light and falls on this depletion layer, then whatever immobile charge carriers are there, they'll gain energy from the photons of the light and they'll give rise to current. Okay, so here as you can see here, this is the symbol of our photodiode. And once I have reverse biased it, and if I make a resistor in the circuit, then you'll observe that there is flow of current. Your photodiode, it will act as a conductor. And in as you can see, if you look at the construction of photodiode, in this figure it will show construction of photodiode. And as you can see here, when we are talking about its construction, it's a small device, okay, and physical appearance, it will be very small. And what we have done here, PN junction, okay, of course this junction, this device, it has got its PN junction. And where we'll keep this PN junction, it is placed inside a glass material. So this PN junction, it is placed inside a glass material. And why we are keeping it in glass material? Because we want to allow the light energy to pass through it. We want light to pass through the glass and it should fall on our PN junction diode. And what we'll do here is, because we want to expose light only at the junction, that is nothing but depletion layer, then what we'll do here is the region, okay, the glass region which is near the junction, okay, we'll leave it as it is. But whereas the other region, other portion of the glass material, we'll paint it black or we'll metallize. Metallize means we'll coat it with metal. Okay, and as I told you, this particular device, so its size is very, very small. So it is of very small dimension. And current flowing, it is measured in microamps by connecting this photodiode to an ammeter. And if you look at this figure, if I talk about this PN junction, usually this PN junction, whatever PN junction we are using in photodiode, this PN junction, it is formed by diffuse junction type. Right? So this is a diffused junction type PN junction. In diffuse junction type, what we have done, we have taken a thin wafer, N-type thin wafer. We kept it in a furnace, and then we are exposing this this N-type wafer to gas of boron atoms. Then you will have diffusion of boron atoms on the top layer of silicon or germanium, which is your base material. Then this top layer, it will become P-type, and bottom layer, it will become N-type. So here also, as you can see here, down I have N region. Okay, on top I have P region, which is exposed to gas of boron atoms, and boron atoms, they got diffused onto the surface of germanium or silicon crystal, because here I have taken silicon crystal. And of course, this part which is shown by green color, this green color, it shows our depletion layer, or simply it is called as junction. Okay, so this green part, it represents our depletion layer. We can also call it as depletion layer. Okay. And down, bottom surface of this N region, it is coated in such a way that it acts as cathode. It acts as cathode, which is negative, right? And then top. So if you look at this top P region, it is coated in such a way that it will here it is connected to anode. So here it is cathode and this one is anode connected, and of course this is a depletion layer. And as we were told that this entire PN junction, it is kept in glass. So it is covered with glass. And what we'll observe here is entire portion, not entire portion, leaving small portion where we want our light material to get inside and fall on this depletion layer. This much part it is not painted black or it is not painted with a metal, whereas the rest portion it is painted either with metal or black. So small region, in order to make radiation enter or fall on depletion layer, we are just keeping it like this, whereas the other portion of glass material covering PN junction, it is coated black or it is metallized. And one thing what we have to understand here is there are two operational modes of photodiode. So here, this photodiode, it is going to operate in two modes. So what are those two modes? First mode, it is called as photovoltaic mode, and second mode, it is called as photoconductive mode. So what is photovoltaic mode? In photovoltaic mode, we are not going to apply any external voltage. So zero bias mode. What do you mean by zero bias mode? Where we are not going to apply any external voltage. So no external reverse potential is applied. Simply what we are doing, simply we are exposing a reverse bias, simply we are taking a normal PN junction diode and we are exposing it to light. Then what you will observe here is there will be flow of minority carriers. So there is a current flowing when we expose it to light. But whereas in photoconductive mode, we are applying external voltage. We are biasing our PN junction. So what we are doing? We are biasing our PN junction. And in which mode we are biasing it? We are biasing in reverse mode. And then here we are, what we are doing, just without exposing it to the light, we are seeing that in case of this, when depletion layer, when we have our light falling on this depletion layer, then we have flow of increase. Actually, there is increase in reverse current. So in what way these two modes are different? In photovoltaic mode, there is no application of external voltage. Just will expose our depletion layer to light. Then whatever immobile charge carriers are present in the depletion layer, they'll gain energy from photons of that light and they'll give rise to current. And that current, it is because of flow of minority carriers. Whereas in photoconductive mode, what we'll do, we'll apply external voltage to PN junction, and we are going to apply that external voltage in reverse mode. And then we are going to expose our depletion layer to light. Then you will observe that current which is flowing across the PN junction, it will be more compared to photovoltaic mode. So there are two modes. One is without applying any external voltage. Second one is by applying external voltage, we are exposing it to light, and our output will be our increase in reverse current. So this is about the construction of photodiode. Now coming to working of photodiode. So as we know that first, when we talk in terms of its characteristic, so when I take a characteristic of PN junction diode, suppose this is the characteristic. Suppose this is our reverse voltage, which is negative, and this is our reverse current. And usually we'll measure our reverse current in microamps. So we'll measure our reverse current in microamps. And here, what we'll observe here is first, suppose we have not exposed our reverse bias voltage to light, then very small current flows across the diode. So this is how we have our current. And at high reverse bias voltage, we know that here breakdown takes place. So this is called as breakdown voltage. At breakdown voltage, what you will observe here is at very high reverse bias voltage, your reverse bias diode, it will start conducting. But it is very dangerous to go to that very high breakdown voltage, because your diode, it is going to get damaged. So generally we avoid going to such high reverse bias voltage where breakdown takes place and where we have large reverse current flowing because of avalanche effect or multiplication of charge carriers. And this current, when you are not Okay, when we have not exposed it to light, this small current which is flowing across the reverse bias diode, it is called as dark current. So it is called as dark current, as you can see. So in photodiode, when very small reverse current is flowing, that current it is called as dark current. And why it is called as dark current? Because this current is totally because of flow of minority carriers, and this is flowing when there is no exposure to radiation. So why it is called dark current? Because we are not exposing it to light. This is the current which we are going to get when we are reverse biasing a diode. Okay, now next, we know that already I have explained when we take our PN junction, when we reverse bias it, then we have seen that these electrons which are in N region, they are attracted towards the positive terminal. Similarly, holes in P region, they are attracted towards the negative terminal, and they'll move away from the junction region, thereby increasing the potential barrier. Okay, so if you see this junction region, in junction region, there will be formation of immobile charge carriers. Now, as you can see here, these black ones, they represent your immobile electrons which have migrated from N region and which have lost their energy to holes. And whereas these particular plus sign which are surrounded by circle, they represent your migrated holes from P side which have lost their energy to electrons. So these are charged. We have plenty of charge carriers in depletion layers, but they are without energy. And then what we are doing, we are exposing it to light. Then what happens to these immobile charge carriers? So here, first when I talk about these immobile electrons, suppose if we try to explain in terms of their energy level diagram. Okay, so now suppose I'm talking only about these electrons, immobile electrons. So what do you mean by immobile electrons? Electrons which are present in the valence band. Okay, and then what we are doing, we are exposing these immobile electrons or electrons in the valence band to this light. So here, light is nothing but having energetic photons. So what happens here, these photons, they'll go and strike these electrons in the valence band, or these photons, they are going to transfer their energy to electrons which are present in the valence band. Then what happens to these electrons? These electrons, they'll get excited to conduction band. So once they get excited to conduction band, what will happen here? Here holes are generated in valence band, and here you will have free electrons in conduction band, and this phenomena, it is called as generation of electron hole pair. This phenomena, it is called as generation of electron hole pair. What is generation phenomena? Where electron in the valence band, it will take energy and it will get excited to conduction band. So for one transition, we are going to get one free electron and one free hole. So depending upon how many number of transitions are taken from valence band to conduction band, we have generation of so many number of electron hole pairs. So that's why what you will observe here is, so when we expose them to light, there will be increase in reverse current. So here, and what you will observe here is, and this reverse current, it is very much dependent on intensity of light which is made to fall on this depletion layer. So when you keep on increasing your light intensity, you will observe that your reverse current is also going to increase. So here, as you can see from this characteristic curve of photodiode, so this is going to clearly explain this characteristic. So if you look at this figure, so in this figure, here we have our reverse bias voltage. We have taken first reverse bias voltage versus this reverse bias current. So here we know that reverse bias voltage, it is negative, and of course this is current which is measured in microamps. So it is measured in microamps. Now what we are observing here is, we are talking about current before its breakdown voltage. I have considered current before its breakdown voltage. We know that when we go for large reverse bias voltage, then we breakdown of junction takes place. So I have not gone to that high reverse bias voltage where breakdown takes place. So here, when you look at this figure, this is our dark current. So what is dark current? When you're not exposing your reverse bias voltage to light. So as you can see, very small amount of current because of flow of minority carriers. Now, what I have done, I started exposing it to different light intensities. So what exactly is this? Here, these are of different light intensities. So here we have exposed them to different light intensities. So when you expose them to different light intensities, now first, so here if you take this one, this first case, here it is of less intensity. So as the light intensity it keeps on increasing, what is happening to current? This current, as you can see here, this reverse current is increasing. So this reverse current, it kept on increasing. So as light intensity increases, reverse current will also increase, because what you will observe here is when light intensity is increasing, then a number of photons, more energetic photons will be there, then more number of charge carriers which are present in the depletion layer, they'll become mobile. So number of immobile charge carriers, they'll increase, converting to mobile charge carriers will increase once we keep on increasing our light intensity. Okay, so this is very important characteristic of photodiode. And what you're going to observe here is, if you see here, current is proportional, or current, it will increase with luminous flux. So when we keep on increasing our light intensity, so and when we are talking about characteristics of photodiode, as you can see, when our reverse bias diode, so if we have taken our reverse bias diode, so this is P type and this is N type and this is our junction layer. And here we have immobile electrons and holes accumulating in the junction layer. And when we start exposing it to light, and depending upon the light intensity, what you will observe here is number of charge carriers becoming mobile will increase. So that's why we'll observe that current is proportionally going to increase with luminous flux. Luminous flux means it is going to increase with light intensity. So as light intensity keep on increasing, then current will also increase. So this is one unique characteristic of photodiode. So what we are observing here is reverse current is directly proportional to intensity of light. So when intensity of light is going to increase, then reverse current is also going to increase. And what exactly is happening here? What is the main phenomena behind the working of photodiode? Here principle is generation of electron hole pair. So here we have generation of electron hole pair, where in depletion layer we have our electrons in valence band. So those electrons, they are without energy. Now these electrons are being exposed to highly energetic photons which are coming from the light. And these electrons, once they gain energy from those high energetic photons, what they'll do, they'll go to conduction band, and thereby what we'll have, we have per transition, we have formation of hole in valence band and electron in conduction band. So what is the main phenomena here? Generation of electron hole pairs or generation of free charge carriers, which is going to increase reverse current. So this is about the construction and working of photodiode. Now, if we take photodiode, there are two types of photodiode. So here, there are some disadvantages with our normal photodiode. In order to overcome that disadvantages, we have created two more types of photodiode. First type, it is called PIN, or simply it is called pin photodiode, and second type of diode, it is called as Avalanche photodiode. So now we are going to see what exactly is this PIN photodiode and Avalanche photodiode. So before going to that, we can just have a glance where exactly these photodiodes are used in day-to-day life. So you'll find that photodiodes majorly they are used in counters, and they are used in switching circuits, counters. Okay, so because we know that they'll give signals, electrical signals, only when they are exposed to light. Suppose if there is obstruction to that exposure to light, then they will automatically change in the electrical signal. So by taking that property, they are used in counters. And of course, these photodiodes, they are used in optical communication system. So in optical communication system, what we'll do, here we know that these optical fibers, when we are sending information through optical fibers, our information, it has to be in optical form. So first, before this optical fibers, we go for laser source, not only laser source, a light source, which is going to convert any type of information in light form. And after we have transfer of information through optical fibers, at the other end of optical fibers, we'll go for this photodiode, which will try to convert our information which is in optical form to electrical form. Okay, and also they are used in encoders as well as logic circuits, and they are used in burglar alarm systems. Okay, because what exactly happens in burglar alarm systems, until exposure to radiation is not interrupted, the current flows. So here, suppose at the door I have fixed a photodiode. Okay, so as long as there is no person at the door, there won't be any obstruction to the light, and there will be flow of current. Suddenly, suppose if someone comes at the door, and because of obstruction of light falling on the photodiode, then there will be obstruction in the flow of current. And when there is obstruction, then automatically there will be one alarm which will start sounding, and from that we can make out that there is some there is some new person who has come to our homes. Okay, so because of that obstruction of light, alarm will automatically start. Then we can go for any unknown person entering in our home. Okay, so this is about the applications. Now coming to first type of photodiode, PIN, or simply it is called as pin photodiode. What is the main principle in photodiode? In photodiode, we have seen that we'll have depletion layer. So what we have done in photodiode, we have taken P type and we have taken N type, and we have our depletion layer, and in depletion layer we have lot of immobile charge carriers. So here we have lot of immobile charge carriers, and where we'll make our light to fall on this photodiode, we'll make our light to fall in the depletion layer. Right now, what you will observe here is, in this PIN photodiode, we'll try to increase width of the depletion layer. So here we are trying to increase width of depletion layer. So width of depletion layer is increased. Okay, and how we are going to increase the width of depletion layer? By inserting one more layer, and that layer it is called as intrinsic layer. So we are increasing our depletion layer by just inserting one more region, and that region it is called as intrinsic region. And what is our main intention behind increasing the width of depletion layer? There are two advantages of pin photodiode. First one is fast response time. So first advantage is having fast response time, and second one is wider spectral response. So it is called as wider spectral response. So these are the two important characteristics. In these two ways, it is better than normal photodiode. And because of these two features, we are going for this width of depletion layer. Okay, so in order to know what exactly is this fast response time and wider spectral response, first we'll just have a quick glance at construction of this PIN photodiode. So as you can see in photodiode, this PIN photodiode or pin photodiode, it's a photo detector in which depletion layer thickness it is modified so that we can get large amount of photocurrent compared to normal photodiode. So here we are trying to get more photocurrent, okay, compared to normal photodiode. And what is our main intention behind increasing thickness? Here thickness is more so that surface area on which light is falling also increases. So what is our main intention behind increasing the depletion layer? So obviously this area will be increased, depletion area will increase. What do you mean by area of depletion layer being increased? It means that number of immobile charge carriers will also increase. So when many number of immobile charge carriers is there with light, so they will become mobile, and then they will be increasing the photocurrent. So here conversion efficiency will increase, and that's why here we are going to get more photo current. And coming to construction, as you can see, it has three regions. So what are those three regions? One is P region, okay, and then P region followed by intrinsic region. Suppose I have taken a silicon P type semiconductor and silicon N type semiconductor. In between I'll insert just the silicon layer, and then followed by N region. And one more thing is, these P region and N region, they are comparatively heavily doped compared to a normal P region and N region which we are using in PN diodes. Okay, and width of intrinsic region, it should be larger. So in order to make depletion layer width more compared to normal PN junction. So this is about the construction of avalanche photodiode. Now how it is going to work. So here also, just like our normal photodiode, they are also reverse biased, and when reverse bias is applied, we know that here depletion layer, it consists of intrinsic region. So here we have lot of immobile charge carriers. So because there are lot of immobile charge carriers, so once we expose them to light, then what will happen? Electron hole pairs are generated because of photon absorption. And here, as I told you, there are two features which are making this pin photodiode better than normal photodiode. As I told you, first one is fast response time. So what do you mean by fast response time? As soon as your light falls on the depletion layer, because there are many immobile charge carriers, so quickly those charge carriers, they are absorbed by the photons, and you have your photocurrent, output photocurrent coming out fast compared to normal photodiode. So that is called as a fast response time. And second feature of this PN photodiode is wider frequency response, spectral response or frequency response. It means that, see, depending upon the wavelength of light which is falling on the depletion layer, then your output photocurrent is going to vary. Okay, if you take ultraviolet light, so these ultraviolet light photons, they are absorbed only by the immobile charge carriers which are present on the surface of depletion layer. So here output photocurrent, it will be slow. Whereas if I expose depletion layer to infrared radiation, so those infrared photons, they penetrate deep into the depletion layer. So here you have within a few milliseconds, you have your output, large amount of photocurrent coming out. So here this output, it depends upon what type of wavelength of light you are making it to fall on depletion layer. Whereas if you go for PN photodiode, whatever may be the wavelength, whatever may be the frequency of light, because here there are plenty of immobile charge carriers, your output response will be good. So it will be independent of frequency or wavelength of the light exposed. So this is about the PN photodiode. Then coming to our second type of photodiode. So this second type of photodiode is avalanche photodiode. So coming to this avalanche photodiode, so this photodiode is also modified in such a way that in order to have large photocurrent. So here, as you can see here, what exactly is avalanche photodiode? Avalanche photodiode, it is a photodetector in which more electron hole pairs are generated because of impact ionization. Now, what is the difference between PN photodiode and avalanche photodiode? In PN photodiode, we are increasing depletion layer, and by the increasing depletion layer, we are increasing many number of immobile charge carriers. That is the main phenomena. Of course, there we have photon absorption based on penetration of photons. We are going to get our output photocurrent. But what is the main phenomena in avalanche photodiode? It is known as impact ionization. So we are going to see what is impact ionization. But first, what we are saying here is, here current photocurrent will be more compared to normal photodiode and PN photodiode because of generation of more number of electron hole pairs. Right here also, of course, electron hole pairs are generated due to absorption of photons, but here multiplication of charge carriers takes place because of this impact ionization. So we are going to see what exactly is impact ionization. Now when we talk about construction of this avalanche photodiode, so it has got 4 regions, whereas in PN photodiode we had 3 regions. One is N and then other one is P, and then both are separated by intrinsic region. Here we have 4 regions. One is N plus region, okay, then P region, and then an intrinsic layer, and then P plus region. Now you may wonder what exactly are this N plus region and P plus region. So this N plus and P plus region are heavily doped regions, and our intrinsic layer is lightly doped. So if I go back to our figure, as you can see, this is N plus region which is heavily doped, and I have P plus region which is also heavily doped, and then here I have P region. Okay, then it is followed by intrinsic region, and this intrinsic region is lightly doped, and we are exposing our light. As you can see, this is reverse biased, and also we are exposing our intrinsic region which is of thick layer to photons. This is about the construction of photodiode. And As you can see, when we talk about working of this photodiode, in photodiode and PN photodiode, once photon strikes the depletion layer, then these photons are being absorbed by immobile charge carriers and they give rise to photocurrent. But if you take this avalanche photodiode, additional factors. So how it is different from normal photodiode and PN photodiode? Here more current is there because of impact ionization or avalanche multiplication factor. So what is avalanche multiplication factor? So for that we should know the phenomena of impact ionization. So what is impact ionization? It is the process in which one energy carrier with sufficient high kinetic energy, what it will do, it will go and strike bonded energy carrier and it imparts its energy to it so that that bonded energy carrier can move freely. So we know that in intrinsic region, suppose if you take intrinsic region, suppose I have taken silicon intrinsic region. In silicon, we know that all its valence electrons, they are taking part in covalent bond formation. So here I have silicon, and here I have all the electrons taking part in covalent bond region. So in the intrinsic region, we have electrons, but all of them, these electrons, they are taking part in covalent bond formation. And we know that once electron is in covalent bond formation, it is a bonded electron, it's not a free electron. Now what you will observe here is, because of photon absorption, suppose I am able to get activated electron. So this activated electron, it will go and collide with this bonded electron. Okay, it will then making this covalent bond break. And once there is breaking of covalent bond, then what will happen here? So once this covalent bond breaks, so here once our covalent bond breaks, then what will happen here? Then these electrons, they'll come out of their bonds and we'll have plenty of electrons, multiplication of electrons taking place. So here we have multiplication of electrons. So as you can see here, so here just one charge carrier with sufficient electric energy is enough in order to break these covalent bonds and giving rise to multiplication of photons. So this leads to higher concentration of energy carriers and we'll get higher magnitude of current. So this is about the charge carriers. So what we have done, so we have seen our three types of photodiodes. First one, we have our normal photodiode. So what exactly is our normal photodiode? In normal photodiode, just we have taken our PN junction diode made with silicon or germanium, and then we have reverse biased it, and then we know that when we reverse bias PN junction, then its depletion layer will increase, and then what we are doing in depletion layer, we have immobile charge carriers and we are exposing the depletion layer to light. Then the photons from the light, they will go and strike immobile charge carriers in depletion layer, thereby increasing the reverse current. Whereas in PN photodiode, what we are doing, we are inserting one extra layer, intrinsic layer, in between P-type and N-type. And what we are going to do, we are exposing this intrinsic region to light. And because compared to our normal photodiode, here we have the region where we have many number of immobile charge carriers. So when photons go and strike on that intrinsic region, so more number of charge carriers will get activated, and here photocurrent will be more compared to normal photodiode. And whereas in avalanche photodiode, due to its construction, where it consists of the four regions, where we have P and N regions being heavily doped, followed by P region, and then we have our intrinsic region. Because of this particular construction, what you will observe here is, if you are able to get one activated electron, this one activated electron, it is going to knock out electrons from covalent. It will break covalent bonds, giving rise to some more activated electrons. These activated electrons, they will knock out some more electrons from covalent bonds. So here breaking of covalent bonds takes place, and here we have plenty of electrons giving rise to photocurrent. So this is about these three different types of photodiodes. I hope you are able to get clear clarification about difference between normal photodiode, PIN photodiode and avalanche photodiode. So I'm going to end my session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.